When you're making IoT devices, you may want to come up with a single Wi-Fi implementation that you can use across all your devices. Inherent in that is that you may want to invest some time to make sure you're doing it well, since it's going to be used in so many places. Are you calling Wi-Fi status every time in the loop, or are you running it on a timer and checking every 5 seconds to find out if you're still connected to Wi-Fi? Are there any other ways you can do this? I was always a little uncomfortable just seeing this Wi-Fi status function and wondering, how long does this take to run? How much is this slowing down my loop? And if you think, well, I'm doing it every 5 seconds, it turns out that doesn't actually save you much time. I sat down to get some perspective on all these different options, and by that I mean, how long do they take to run? I think there's a better way to be checking your Wi-Fi status. It involves making use of the events that are provided by your Wi-Fi library. You may wonder, is Wi-Fi status that bad? No, it's actually pretty fast as well. But is it the fastest? No, it's not even close. In this video, I'm going to run down the different options for checking your Wi-Fi status, and I'm going to show, using some code, how long each take to run. With that, I'll give you a recommendation, and then I'll show you the most basic implementation for how you can use events to get the fastest Wi-Fi check possible. In this video, I'm going to walk through the methodology for how we can time these different status checks and compare them. Then I'm going to set up a program to actually do it. We're going to run through all the different options and see in real time how long each takes. After that, we can discuss the implementations and come up with a recommendation. I'm going to recommend you start using Wi-Fi events. I'll show you the most basic implementation for how we can use events to check our status. It actually can be done in one page. It's not that much. Lastly, I'm going to wrap it up, which means do some housekeeping on the code base, show you that it's going to work with Arduino, and then put it in GitHub for you to use. On methodology, we're not going to use millis, we're not going to use micros, we're going to use the actual CPU cycle count to determine how long our different options take to run. Platform I/O and Arduino IDE both use two different functions to get cycle count. I'm going to be working in Platform I/O today, but then we're going to wrap it up and put it into Arduino as well. There's two different functions we can use to check the CPU frequency. These both return the same thing. They both work in Platform I/O and Arduino IDE. I'm just going to use the get CPU frequency because it looks a little cleaner to me. The ESP32 should be running at 240 megahertz. I'll confirm that with that function call. If you're doing 240 million thousand cycles a second, that means you're doing 240 cycles a microsecond. Rearranging that math, it takes 1 divided by 240 microseconds to run one cycle. If you want to convert to nanoseconds, you'd multiply it by 1,000. This next part's not a joke. I had to go back to 7th grade math, Mr. Cartmel, to work out this problem in my head. So if one cycle is 1,000 divided by 240 nanoseconds, and we can find that x iterations takes y cycles, then we can divide both sides by x, cancel out x, and that means one iteration will take y over x cycles, which is the same as saying y over x times 1,000 divided by 240 nanoseconds, where y equals the total number of cycles and x equals the total number of iterations. So our time per iteration in nanoseconds is the number of cycles divided by the number of iterations times 1,000 divided by 240. The playlist I'm going to run down, the first one is the obvious. Wi-Fi status either equals WL connected or doesn't equal WL connected. The Wi-Fi.h docs also reference a Wi-Fi is connected. I guess it's supposed to be a more convenient way to check. It is less code, but I don't think it's actually even faster. What if we're using some Boolean values that we can check? You would guess that checking a Boolean is going to be faster than checking a function, etc. I'll go through the different options and let's see what we get. Before we go forward, I want to preview 3 concepts that I needed to get my arms around before getting through this set. The first is compiler optimization. Of course, the compiler is going to try to optimize how the code is structured. What I've found is that any change to your code at all would actually change the results from your tests. Let's say we are running some code, and before the code starts, we get a cycle count. After the code runs, we get another cycle count. We take the difference. That's how long the code took to run. I found that if you add a line of code anywhere else in the program, the cycle count that you get through here is now different. This is very black box, but it's not flaky. I cannot begin to explain the decisions the compiler is making, but I can tell you that the results are very repeatable. Whenever you change the structure, the timing will change, but will do so very repeatably after that. The next thing is dead code elimination. The compiler will actually recognize that you have asked it to execute code that serves no purpose. It will simply ignore it and not put it in the binary at all. So you will see examples in the next few minutes where we write code, we try to clock that code, and we get a time of 0 because the compiler just threw it out. And the third thing is branch prediction. The processor can parallel process both the investigation of a variable value and the code that's supposed to be executed accordingly. It thinks it knows which way you're going and starts to execute code. If it turns out it's right, you win. If the prediction is wrong, then it needs to throw out that work and start over, and this is apparently a very expensive process. When you know that your value is going to change, when you expect it to change, you can declare the variable volatile, and that will tell the compiler, don't do branch prediction on this value. In doing that, there's a side effect where it also tells the compiler, look, you don't know what the value is going to be, so don't subject this to dead code elimination. I would expect that everything I said wasn't totally clear, but when you go through the demonstration now, I think the things you see are going to make more sense as they happen. We'll start with our basic setup and loop. I'm going to push loop aside. We're not even going to use it. Because we're going to be serial printing, we would need Arduino.h. But I already know we need Wi-Fi.h, which includes Arduino.h. We'll declare a start and a stop. And then we're going to log. This is the basic program structure. From here on out, it's just filling in some details and all the other complexity I have to explain. I'm going to put the logs on a separate tab so it doesn't pollute our main. Let's just start by printing our start and stop cycles. I will include Arduino.h here because we're serial printing and not including Wi-Fi.h. You can see already we got one cycle. The difference between line 10 and 12 is one cycle. I'll start to manipulate the values and add more information. We expect get CPU frequency to be 240. We know we can calculate the total time using the frequency of the chip. By the way, I got an error on this math for some reason, and I think it's because total cycles is a uint64, but frequency is just an int. When I cast frequency as a uint64, that fixed the problem. I don't understand why I had the problem, but this fixes it, so good enough for now. So we have one cycle. We expect that to be the 4.17 nanoseconds. But we get 4.0. That's because we divided an integer by an integer, which can only return an integer. The solution is to cast either the numerator or the denominator or both as floats, and then this will return a float. You'll see I've got these 4 lines I'm printing. One is going to be 0. The other 3 are going to have the decimal value. My point is, we need to cast the numerator of our function as a float for this to work. And by the way, this uint64, I could have just declared it above, so I will do that. We run it, and there you go, 4.17 nanoseconds. That's what we'd expect. Let's add some iterations. Instead of just running this once, let's run it 10,000 times just to make sure any random variations are washed away. Notice that our while loop is inside of the start and stop definitions. I'm going to create these green lines just to kind of identify that this is the space that we want to test. Let me send iterations through to our log. I'll update the prototype and then the definition as well. I'll change processing time to total time. I'm going to drop the 1,000 here so we can look at it in terms of microseconds. And then for time per iteration, I'll put the 1,000 back so we're in nanoseconds. Then I'll divide by iterations to get the time per iteration. Okay, it says this is a total of 20,000 cycles or 8 nanoseconds per cycle. But that's actually including all the overhead of our actual while loop. When I move this variable, notice the total time changes. Now we're down to 1,000 cycles. Because the count variable was in the global space, apparently the compiler is less confident it can predict its value, and its branch prediction runs differently. What we can do is make count volatile and say, just don't do any branch prediction at all. And now the time per iteration goes up quite a bit because we're telling it, don't optimize, just read this value every time. You see that this has 110,000 each time it runs. I'm going to grab that value and I'm going to define a benchmark. We want to test the code inside the green lines. So we want to subtract the time it takes for everything else to run. That time it takes for everything else, we're going to call our benchmark, and from there we can actually analyze our desired code. Instead of total cycles, we're now looking at net cycles. I'm going to get rid of this frequency. We already know it's 240. Now look, our total cycles changed even though our code in the brackets didn't. As I mentioned, every time we move code around, the optimization changes and so does the time. The difference between these two cycle counts is not even 1%. It doesn't change it greatly, but it changes it a little. I will simply update the benchmark. There. Now, the time it takes to execute what's inside the green lines is 0. I'm going to set the benchmark to 0. We don't care about the count time for count. We need to do something meaningful in this loop, but we are not ready yet to do that. I'll show you what I mean. I'm going to add a second green space. Let's call the second one loop and the first one setup. We need to define some variables before we test them in the loop. I'm going to run it again. We changed the code, albeit slightly, but we're going to get a new benchmark. I'm taking this 966 and putting it in. That came down because we got rid of volatile. If you look, when I updated the benchmark, that actually changed the benchmark. Let me go from 966 to 965. Fine. Now we're at 0 again. I would start to test, but we've got to work out some problems first. Look, I just added some code and got 0 nanoseconds. That conditional didn't work. What if I put a variable in our space and toggle it on and off? 0 nanoseconds. What if I attempt to toggle that variable inside of a conditional? 0 nanoseconds. This is the dead code elimination. Compiler recognizes we're trying to do work, and yet that work doesn't serve any purpose. If I just take the dummy variable and later in the program serial print it, we now get a meaningful number. This code was actually run. I'll go ahead and update our benchmark. If we put it inside the conditional, another overflow, because we changed our benchmark. Let's update it one more time. There, 0 seconds. The conditional didn't run at all because the compiler knows it's just going to always be true, so it just eliminates it. Having a dummy variable that we toggled and print gets us to where we're ready to actually start testing conditionals that are meaningful. Let's go through our playlist. I showed you that if true gets thrown up by the compiler. If we create an isConnected variable we want to test, it's the same thing. It's a value the compiler knows is true, and it will throw it out. The trick is to instead create a result the compiler cannot predict. Because the compiler cannot predict the value, it must evaluate it every time. And now look, 4.17 nanoseconds. It took one cycle to determine that that was true. If we switch to our famous Wi-Fi status equals or doesn't equal WL connected, it now takes, it gives me a result I didn't expect because we're not actually running Wi-Fi yet. Let's go ahead and fire up our Wi-Fi connection and check that value again. And now we're at 1100 nanoseconds, which is what I've seen several times in the workup to this video. The Wi-Fi.h provides some sort of convenience function, which is just is connected. I guess it's less code, but when you test it, it actually takes longer to run. I wouldn't call that valuable. Some people say, hey, I'm not going to check this every single time in the loop. I'm putting it on an interval. But if we actually craft an interval and test that, we're not even going to get to 5,000 here. So we don't have to do the Wi-Fi check. The question is, how long does it take to check the interval? And that is still almost 1,000 nanoseconds. So checking your Wi-Fi status on an interval is not particularly helpful. I want to compare a Boolean that belongs to a class, my Wi-Fi tools in particular. I want to compare that to the isConnected Boolean that I created right in the function. And I have to stop here. Long story short, I could not get the compiler to recognize this. In previous tests working on this, I absolutely could. But today I'm getting 0 nanoseconds every single time. So I'm just going to put in volatile on that value. And you see we get 20 nanoseconds. The slowest possible way to check this value is with a volatile declaration. And yet it still only takes 20 nanoseconds to check versus 1200 for Wi-Fi status. I think there's something I'm missing in my structure. In fact, I think that this Wi-Fi tools isConnected will behave the same as the plain isConnected Boolean, meaning it's going to take 1 or 2 cycles to check, not even that 20 nanoseconds. While we're here, I just want to throw in a digital read. How much does it cost to check a pin? I don't believe it's 170. I think what happened is we didn't execute the code inside the brackets because it was false. If I make this conditional true, you see we get 190 milliseconds. The implications of all this, let me show you my Scratchpad. This is not formatted. I just had been running these tests several times. Actually, today what I built up was from scratch, and I got very similar results. These different results are corroborating each other. Let's look at it one more time. And what I see here is that using the Wi-Fi status or Wi-Fi isConnected is about 50 times at least more expensive than just using the Boolean values that we can get from events. Regarding doing a Wi-Fi check on an interval, don't even bother. It takes almost as long, and you're now waiting, let's say, 5 seconds to get that Wi-Fi status. You might as well just check it every time. So what of this Wi-Fi status time of 1200 nanoseconds? Look, 1 microsecond ultimately is not a big deal, right? If you're just doing temperature data or something, it's fine. I would just say, if you don't care about speed as a priority, then you might as well at least check every single time in the loop. But lastly, yes, you could just stick with the Wi-Fi status check, but setting up events is so simple, why wouldn't you just do that? I'm going to show you here a basic implementation of events. We're going to create an event handler, and we're going to use that to set our isConnected Boolean, and that Boolean is going to be checked in the loop. Here's a basic Wi-Fi setup in Arduino IDE. You see we begin serial, and I'm just putting the credentials directly in the Wi-Fi begin. Then, in the loop, we're checking if we're connected, and we either print connected or disconnected every second. I compile, and you see here it's working. Now, before Wi-Fi begin, I'm just going to tell the Wi-Fi module that on an event, I want you to call an event handler, which has not been defined. So I will come down below, and I will define it. This event handler is going to receive an event from the module. Let me create my isConnected Boolean. If you see my previous video on Intro to Wi-Fi Events, I have a full explanation of what's going on here. But in summary, of the several events that this event handler may receive, the 2 we care about, Arduino event Wi-Fi stay got IP means we are connected, An Arduino event Wi-Fi stay disconnected means we are disconnected. We're no longer going to check Wi-Fi status. We can just check our is connected boolean. We're disconnected at first, and then we're connected. Let me add some serial prints to the actual events so we can see when they occur. We turn the device on, we get a connect event. I unplug the router, we get a disconnect event. In fact, we get several disconnect events. I plug the router back in, and eventually we end up getting a connect event, and we're now connected again. It's that simple. We just set up the fastest Wi-Fi check you can possibly have. Now it's time to wrap it up. I didn't show it in the video, but I just cleared out those green blocks, the setup and loop that has our test data. I'm leaving in the dummy variable because, as I showed you, without it, you get the dead code elimination and your test doesn't even run. To wrap this up for Arduino, I'm going to do something a little different. You know, in Arduino, the main sketch file has to match the folder name. So I'm going to create a folder called clocker, and then I'm going to change main.cpp to clocker.ino, log.cpp to log.ino. Now we've got the file names we need for Arduino IDE to work. I've got to replace these function names. As I mentioned in the beginning, Arduino IDE exposes a different function you can use to check cycle count. I compile, and there it is. This is now officially Arduino IDE friendly. I'm going to push this to GitHub if you want to review the logic. The link for the repo will be in the description below. We just got into a bunch of compiler concepts that I did not expect to, but I did think they're pretty interesting. And now you see a framework for how you can test the performance of any functions you may write. But I think the big takeaway is that Wi-Fi status is fine. It's not that bad, but it's also unnecessary. There's a much faster way to check Wi-Fi, and it's not that hard to implement, so why not do so? I'm just scratching the surface in terms of what I want to cover on IoT. Right now we're doing ESP32 firmware, but I'll be transitioning to other concepts. I'm looking at the whole package for how do we get our devices connected to the internet and control them. If this interests you, subscribe to make sure you always get the latest. This should be going for a while. In the meantime, I'm Larry. Thanks for watching, and I'll see you next week.